Okay, we have Andan Lee of Caltrans. Andan, please go ahead and ask your question.
Actually, I don't have a question, but I would like to give some comment about the study on gravity soils. Actually, I know that not so many people study on gravity soils because of so many limitations, especially in the lab, because you need a very big particle, big sample size. Um, uh, so I give some comment about that since my research is on, I also spent my life with gravity soils. So I know a lot about gravity soils. Uh, um, so one of the thing is 20 years ago or 30 years ago in Japan, we already developed big triaxial tests. And also, we also developed the true triaxial test we perform of our gravity soils. So 25 years ago. And and mainly we study in the laboratory test. We compare between the dynamic soil property and static soil property to find whether any correlation between the shear wave velocity and the shear modulus or Young modulus in the lab or not. So because we have a very good equipment, we can measure very small strand, so we can compare it. So that is the comment I have. And 2 years ago or 3 years ago, I know that Professor Kokusho in Kyoto University in Japan, he did a very good summary about gravity soils and sandy soils, and he published in the in well, in some journal. I already put in the chat, and I hope that someone, if already review, then it's good. But if not review, so I take some chance to look into it. That's all my comment about gravity soils. Thank you.
Any response to Andan or any comment on it?
Just say we're certainly familiar with it. I'm sure Ada is as well. All of our students read it, and it is probably the most comprehensive experimental data set in literature on the triggering aspect. So thanks.
Mm-hmm. There is a question from Cathy. Is there anything that structural engineers would benefit from becoming more informed when making decisions about foundation design? Any of you can answer? It came in the chat box rather than the Q&A, but yeah, you can see it. Yeah.
That's me. I'm Cathy Rye, and thank you so much for sharing, because I do often run into cases where I'm thinking, wow, I wish I knew more about geotechnical engineering. And I know that there's probably plenty of geotechnical engineers on tap. It's just more, is there anything that drives you crazy that you wish structural engineers would know more, that you're constantly answering over and over and explaining over and over again?
From their smiles, it looked like there is a lot, but I would let them say that.
I can try and answer that. It's a great question, first, Cathy. I think so many problems involve soil structure interaction, and we pretend like there's a clean dividing line where we try and hand off to each other between structural and geotechnical engineers. And I think that we really need to work together because the structure influences the way that the soil behaves. There have been cases where vibrating structure will impose stresses on the ground that may cause it to liquefy, which in turn influences the response of the structure. So it's a complicated thing. And then I guess with respect to gravel liquefaction, maybe I'll ask a question for Ada or Jason. I think that impeded drainage is a huge factor when it comes to liquefaction of gravels. And I'm just curious whether a mat foundation or some other kind of concrete barrier that might prevent flow of water has been observed to cause liquefaction beneath a structure where maybe none has been observed in a more free draining condition in the free field.
Well, if I can just quickly, for the previous question, in terms of structural engineers, just add that something I think that's important to keep in mind is that in geotechnical engineer, I'm sure in other disciplines as well, there is tremendous variability in the response. And so it's very difficult to be asked for a value rather than a range and have this understanding that a certain site is not going to respond in the same way, depending on the subsurface conditions. If I can just quickly, and then I can pass it on to Jason, just answer Scott's question with some of the observations we've made, at least not necessarily for mount foundations with buildings, but in ports where there tends to be, like a concrete layer at the top. It has been shown that definitely caps your material and will, restrict this immediate drainage that would have otherwise to happen in some of the more uniformly graded materials that you would expect would have larger hydraulic conductivities.
Yeah, I'm totally agreed with that. I think there's two scenarios where gravelly soils can liquefy. One is the scenario where it's well graded sufficiently that it has enough sand in it that the permeability is on the order of sands, even though there's larger particles. And in that case, then you can certainly generate the excess pore pressure. The second one being a poorly graded but very coarse soil, so the permeability or hydraulic conductivity is very high. And then you may have some rearrangement if you can get some pore pressure generated, and if you have upward flow, then it could be capped typically by a softer sediment on top. I don't know of a particular case history beneath a mat foundation or something like that, though I imagine some surficial coatings or coverings on ports or places like that as a working surface may have also served as a cap.
Armin has a question for Jason. Armin, would you like to ask directly?
I think, sure. Jason, interesting work, and I'd like to congratulate all three studies for wonderful findings today. But I was struck by these differences in excess pore pressure dissipation rates. And, it wasn't super clear. Maybe I missed it, what the differences in relative density were, or maybe the relative density was kept constant, but they had much different void ratios. But based on the cone penetration test results and shear wave velocity, there were some differences between the four soils. And so it just leads me to speculate whether there's sufficient differences in the geostatic stress state to maybe explain some of the coupled fluid mechanical responses between these specimens.
Yeah, it's a good catch, Armin. If you look at the gradation, from the gradations of the material, the soils were designed so that the D10 is about the same. So at a first pass, you could say on Hasen's equation, they should have roughly the same permeability. However, going from the most poorly to the most well-graded soil in the study, the permeability decreases more than by a factor of 2 just based off of a void ratio reduction, even though they're both at the same relative density. And so that lower permeability you would expect for the pore pressure dissipation to take a larger amount of time. However, the absolute density of the more well-graded material is higher by a decent amount. And more importantly than that, the modulus or the bulk stiffness of the material is substantially higher by about 40%. And so as a result, the amount of water flow needed to dissipate pore pressures is substantially lower because the soil has a much higher bulk stiffness.
Yeah, that seems quite in line with what we've observed in other centrifuge test results. And again, thanks. Great work.
Yep. Thanks for the question.